Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of embedded system, and in this lecture I am going to describe the DFG model and finite state machine, where I am going to give you a perception about the hardware software co-design, or what we could say the hardware software trade-off of different kind of embedded system. So let's begin with the lecture. So state machine and concurrent process model. So these are the subject we are going to describe about. So let's begin. The introduction will be is about the models versus language, finite state machine with data path model, using state machines, program state machine model, concurrent process model, concurrent processes, communication among processes, implementation, data flow model, and real-time systems. So these are the topics we are going to cover in this lecture and in the upcoming next lecture. So let's begin. So introduction, what we have here is implement a system processing behavior with processor. For describing the processing behavior using assembly language, another method of describing the processing behavior using high level languages. Both uses sequential program computational model in which instructions are executed sequentially. Increasing the complexity of the embedded system functionality requires advanced computational models. The embedded systems today covers sophisticated applications like cell phones, etc. Common method to describe the system is by means of English language, which is more convenient and not sufficient to cover the complete system. A computation model assists the designer to understand and describe the behavior by providing means to compose the behavior from simpler objects. So let's go to the next slide. The next slide is describing is that models commonly used for describing the embedded systems. First one is a sequential program model. It provides a set of statements, rules for putting statements one after other, semantics stating how statements are executed one at a time. The next one is a communication process model. It supports description of multiple sequential programs running concurrently. State machine model. It is used commonly for control dominated systems. Control dominated system is the one whose behavior consists mostly of monitoring control inputs and reacting by setting control outputs. So let's go to the next slide, and from here we can understand that if we also have to understand the basic differences of these three models. The first one, which is known as sequential program model, where it provides a set of statements, rules for putting statements one after other, semantics stating how statements are needed to be executed one at a time. These are known as the sequential program model. In case of communication process model, it supports description of multiple sequential programs running concurrently. And state machine model, where it is used commonly for control dominated systems. Control dominated system is the one whose behavior consist mostly of monitoring control inputs and reacting by setting control outputs. So these are the three specific program models that we are going to uncover. So let's go to the next slide. Fourth one is the data flow model, which what that means, it is used for data dominated systems. The system behavior consists of transforming streams of input data into streams of output data. The fourth one is the object oriented model. It says that it provides an elegant means for breaking complex software into simpler and well defined pieces or blocks. Suppose the model versus English is the poetry is also English, recipe is a Spanish, and story is also a English, Spanish and Japanese. It means a poetry can be written in English, Spanish and Japanese. The same thing, the state machine can be written in C, C++ and Java. The same thing will be applicable for sequential program, where it also can be written in C, C++ and Java. But when we are talking about the data flow model, it also provides us with the same luxury of can be written in C, C++ and Java. So this is the object oriented model, and these are the analogy. Okay, so let's go to the next slide. Now the next slide have described what is the difference between the model and a language. Now a computational model describes the desired system behavior, while language capture models. A model is a conceptual notation or notion. Is a model is a conceptual notion, while a language captures that concept in the concrete form. A sequential program is a model, a conceptual notion consisting of a set of program instructions for computing something, and a notion as of how to sequence among those instructions. Sequential program can be captured in any of the following languages like C, C++ or Java. Particular language can capture many different models other than sequential programs such as state machine or data flow models. Other languages such as C and assembly language are more suited in some applications. So let's go to the next slide. Textual language versus graphical language. Languages may use variety of methods to capture models such as text or graphics. The choice of textual language versus graphical language is entirely independent of the computational model used. The graphical language uses icons of objects and icons for tasks. Graphical sequential languages were commonly proposed in 90s, 80s, but have not become very popular. The state machine model is often captured in textual language, but it is also commonly captured in graphical language. Okay, the state machine model is often captured in textual languages, but it also commonly captured in graphical languages. So let's go to the next slide. A basic state machine model, which is also known as the finite state machine. A finite state machine model. The system behavior can be described as a set of possible states. System behavior can be described as a set of possible states. A system can also be described possible transition from one state to another state depending on the input values. describe the actions that occur when in a state or transitioning between states. Let's go to the next slide. This is the finite state machine model. Now if you take a close look here, that UDOT, which is the 1000 input, is required is greater than floor, then it will go up. Now if the UDOT value is 0010, the required is equal to floor, it means it will be in the idle state. Now if the condition is this, it will go up. Now if the value is this, then it is going down. Now first, this is in the ideal form. If the required is equal to the floor, this sign is provided us the information that the state in which the data are in will stay in that specific state. And if REQ is greater than floor, it will go up from the idle point. And the same thing also will be acceptable where the REQ is less than floor. The idle in the data, those who are in the idle state, will goes down. Now if EDOT value is 001, the same thing, the doors will open and it stays there. And if the required greater than floor is not equal to this sign is not equal to sign, then what will happen, that in greater than floor condition, it will just get into the same position. Now if required is not greater than equal to floor, it will just jump to this door open state. And if required greater than equal to floor condition satisfied, it will just stay in that state. So what it means, the first, the data will be in this ideal state. As required greater than floor condition met, the value in the ideal state will going up, which goes to the going up state. Now if required is equal to floor, then the data will be stayed in the state. Now if required is less than floor, what will happen, the data will move on from the ideal state to the going down state. The finite state equation can be expressed as 6 tuple. This is the, we'll say, F is less than SI of Hs, and S is the state of states. I is the set of inputs, O is the set of outputs, F is the next state function, and H is an output function. S tends to 0. Mapping current state to outputs, S0 is the initial state. Now if you take a close look here, that required is equal to floor, the data will stay in this ideal state. If required is greater than floor, it will go up to that state. And the same thing, if required is less than equal to floor, it will goes down to this state. Now if required greater than floor condition met each and every time, this data will be stayed in this state. Now suppose the required greater than equal to floor, this specific statement doesn't, the condition of this state doesn't match. So what will happen, the data will goes from this going up state to the doors open state. And this thing in this ideal state, where the data is in the ideal state, will happen if the timer is less than equal to 10. If timer is not less than equal to, if the timer is up to the value 10, the timer will be there. And if it goes timer greater than 10, what will happen, the data from the ideal state will continue itself, and for this condition the doors open and the data will goes to the ideal state. Now if we are talking about the going down state, if required is less than equal to floor, it will be there, and if is required equal to floor, the values goes to the doors open state. And as the timer is less than 10, the doors open state will carry forward itself, it will be in the loop where it continues itself. So this is a finite state machine. Let's go to the next slide. So S is the set OS states, S0, S1, S2. L is the state for inputs, I0, I1, I2. O is the set of output states, O0, O1, O2. Often finite state machine is used to describe the single purpose processor. Often finite state machine is used to describe the single purpose processor. The hardware is synchronous, such as register. Updates are synchronous to clock pulse. The finite state machine FSM every transition condition and with clock. Let's go to the next slide. Finite state machine with data path model. In an embedded system, the inputs and the outputs are Boolean type. This is sufficient for many control system applications. .any as set of states. For more complex data type, the FSM is extended with data path model. The possible FSMD model is a f less than SIOV FH and S0 greater than 1. Describe the machine behavior as a state machine and list all possible states giving each descriptive name. Declare all variables. For each state, list the possible transitions. List the associate conditions. For each state or transition, list the associated actions. For each state, ensure that existing transition conditions are exclusive. Let's go to the next slide. Comparing the state machine and programming language. The state machine model is appropriative over sequential program model for describing control-based system. It encourages the designer to think of all possible states of the system and to think of all possible transitions among the states based on the possible input conditions. It provides the more natural means of computing for each case. In the sequential program model, the system is designed to transform the data through a series of instructions that may be initiated or conditionally executed. It encourages a different way of thinking the behavior of the system. So these are the basic differences of state machine and programming language. So let's go to the next slide. So here we have now hashtag define idle is equal to 0, hashtag define up0, hashtag define dn is equal to 2, and hashtag define open is equal to 3. Now according to the conditioning of this program is void unit control bracket integer state is equal to idle while the condition 1 is satisfied. The loop will move an ideal up is equal to 0, down is equal to 0, open is equal to 1 and start is equal to 0. If required is equal to floor, the state will be an ideal state. If required is greater than floor, then the state will be up, going up. Now if required is less than 4, the state of the data will be dn, down. Now if you just break it, if this break what will happen? Now you just break up. Okay, we will going to break up. If required equal to floor, that condition met and state is idle. What will happen? The program will break itself and it will jump to the, from this condition it will jump to this up condition. Now up is equal to 1 and down is equal to 0 and open is equal to 0. The timer start is equal to 0. Now if required is greater than 4, the state will be up, and if required is not equal to 4, the state will be open. and it will again go. So if any of this condition met first, if this condition has been met, this program will break and it will go to the next this step. Now if required greater than floor not equal to not equal, then this state will activate and this the breakaway from the loop will occur and it will jump to the DN state. The same thing will also be applicable, or yes, I would say that applicable to required greater than equal to floor. Now see, suppose this condition has met. Suppose this condition has met. What will happen? This will jump to this state. Now if any of this condition has met, it will jump to this condition. So this is the clear picture that if any of the condition met first, it will because of this break code, this function will not continue, it will jump to the next will be starting condition. The same thing will also be applicable for this second loop, and in case of third loop where the going down conditioning are applied. Here the up is equal to 1, the down is equal to 0, open is equal to 0, and the timer start is equal to 0. And if required is less than floor, the state will be is equal to DN. And if required is less than equal not equal to less than floor, the state is equal to open state. So again the same thing. Any of this condition, if any of this condition will if got met, if met, then it will break out from the loop, and in this open state, up is equal to 0, down is equal to 0, open is equal to 1. These are the conditioning which has given us the definition of which state we are in, and the timer start is equal to 1. So if timer is less than 10, the state will be in open state, and if its timer is not equal to less than 10, then the state will be in idle state. So the break thing will also happen. So in this way, with each break, each condition will met and will go to the next step. And this is a very beautiful programming, and using that we can describe the total fundamental perception of a finite state machine using this condition. So okay, so this is the function that we first consider the different state value of ideal up, DN, and open, and according to that we have first open a main function which is a void in unit control, and in integer state will be we have assigned it to idle, or suppose we assign idle to the unit control state, and according to that, as the idle state start running, the first any of these condition got met, it will break away from that loop and it will I would say complete the operation of that specific data. If a data has jumped from the idle to the up state, then the conditionings, all the conditioning that we have already fed with or provided with, it will take a very less time to triangulate the situation, because if required is equal to floor, this condition met, it's go break, and the all the operation that is the data need to be performed on will be start executing. Okay, so this is the basic fundamental of FSM. So in this way we are going to end this lecture here. Okay, thank you.